Welcome to Plutus IAS, and today we are covering about azeotropic mixture. Well, azeotropic mixture comes under your unit solutions after talking about your ideals and non-ideal solution. And today in this lecture we'll discover what are they, why they are so distinctive that we are talking about them, and is there anything special about them. So, as for the azeotropic mixture, for the definition part, azeotropic mixtures are defined to be binary mixtures. Binary mixtures that have a definite composition composition in solution and vapor phase and boils at constant temperature. So in this definition there are lots of words. First thing, binary mixture, where the binary means comprising of two species. Then we have definite composition, that means they have a definite mole fraction in solution phase and as well as in their vapor phase. So as per Raoult's law, we represent mole fraction by Y in gaseous phase, and in solution phase it is represented by X. And they boil at a constant temperature. Now, since you are mixing two entirely different species, they both possess different kinds of forces between the solvent and solute forces. So what happens is when we mix together, they also possess different kinds of boiling point. So after mixing, whatever interaction that exists between them, it's very likely that the forces of attraction will cause a shift in their boiling point. So but at a definite composition, when you are talking about, their boiling point becomes constant. So in order to represent it like this, before let's talk about the types of azeotropic mixture we have. The types of azeotropic mixture, first one being called as your minimum boiling azeotropes. Minimum boiling azeotropes. And then we have maximum boiling azeotropes. As the name suggests, minimum boiling azeotropes are those species which boils at a lower temperature. And let's say your solvent has a boiling point somewhere here and solute has some boiling point here. So this azeotropic mixture boils at a temperature which will be lower than either of the solute or the solvent. While maximum boiling point will have an exact opposite condition, where the boiling point of the solution will be higher than between the solute and the solvent. So in general, what we have found, let's say if I have mixed water and alcohol, water is there and I have added some alcohol to it. Now compared to water, alcohol has a much lesser boiling point. So if I boil this solution, alcohol will boil first and then will water. But in azeotropic mixture, we are looking for what composition or ratio I maintain between my two different solute or solvents, so that they both arise at a common boiling point, which can be either above their boiling points of either of the solutions or lower than either of them. Based on that, we have two different graphs. Here, this graph corresponds to minimum boiling azeotropes. Minimum boiling azeotropes, while this one corresponds to max boiling azeotrope. Now, let's say this is your species 1 which has some vapor pressure. This is the pure pressure of species A, and you can also call it P0A. This is the pure vapor pressure of species P. Now what happens is, in this direction you have the maximum mole fraction of A only, while XB exists as 0. When you start moving from this point to the left hand side to the right hand side, the mole fraction of A will start to decrease and reach at a point of 0, while the mole fraction of B reaches its maximum value. So what happens is, when the mole fraction we are trying to increase slowly, we see that by decreasing the mole fraction as per Raoult's law, since the mole fraction of A is decreasing, its vapor pressure starts to fall. This blue line represents the fall of the vapor pressure for the pure solution. But when you mix it with something else, we find that here the slope falls a little further. And this is the region where we say this is the coexistence phase. In this phase, your solute and solvent could exist together and there will be not much appreciable change in the boiling point of any of the species. But at a definite composition that you arise, this species will have a boiling point which will be lower than any of the species. And same goes with this case. Now, based on that, if I ask you which species which I add to the solution will be responsible for a formation of this azeotrope would be. At this point, this is at the center. But if I shift this graph a little, then the mole fraction of A is lesser and mole fraction of B is more. So that means if I boil a azeotropic mixture, especially when it is minimum boiling azeotrope, if I have species B which is responsible of formation of this azeotropic mixture first. So when I boil it, species A will be the one to leave first from the solution in the vapor phase because B has formed the azeotrope. While if I go for maximum boiling azeotrope, I'll find the same thing but in the opposite case. That here, increasing the mole fraction, the vapor pressure of A increases, same goes for B, and at a definite position, I achieve a maximum boiling point which will be above than either of the solutions. Now, since you will find this is the portion here, XA is in the maximum side, this is the side half, XA is in maximum on this side while XB is at minimum. So that means if I add, in this case, A is constituting a major part of the azeotropic mixture. So when I boil this solution, after a certain interval of time, my solution B will be the first one that will get evaporated, while A, since it is forming maximum boiling azeotrope, it will try to remain in the solution. You need to provide higher amount of energy so that you can get a definite amount of vapor pressure out of it. So I hope this would have cleared your doubt what are azeotropic mixtures, how they are formed, and especially how to read a graph regarding your azeotropic mixtures. In case of any doubt, you are allowed to add them to the comment section and we'll get back to you. Or if there's any specific topic that you want us to make a video regarding that, you can also add it to the comment section. Thank you for joining us today. That's all for now.